Welcome back. Hopefully you've had a bit of a chance to take a look at some examples of some of the things that we were looking at last time. Before we get into infinite limits, which is the next topic we're going to talk about, I just want to really briefly run through a quick recap and an example. Hopefully this stuff is all just a reminder for you, though. When we're looking at limits, we talked about how we want to look at left versus right side limits. What happens as our x value approaches on the left side versus what happens on the right side. And we know that a limit only exists if both the left and the right sides end up equaling each other. We call that limit a two-sided limit because both of those sides have to be matching up. We can approximate these things numerically. We can literally just plug in some test values that are smaller than the x value we're looking at if we're looking at left side, or bigger than the x value we're looking at if we're looking at the right side. Or we could look at a picture of a graph and we can try and follow what the pattern of y values is doing as we follow the graph on the left of that x value or on the right of that x value. Graphically, things are a little bit trickier, I find, for students, so get some practice on that. Make sure you can read graphs. Try playing with that example that we had online. We also talked about how we can evaluate limits instead of approximating them by, right now, we're just kind of plugging in the x value and seeing what happens. We notice that for easy limits, basically we can plug things in and it'll just spit us out a number, and that works out really nice. We're calling those easy limits because there's just not a lot of work to do. Every now and then we get this indeterminate form, 0 over 0, which tells us that we've got to go back and do some algebra and see what we've got. You've probably seen an example of this kind of piecewise function here. Let's just take a look here at what happens if we look at the limit as x approaches 4. And I apologize, my handwriting is not that great today. It's not great ever, but today it seems like it's pretty bad. What we're going to do is look at a left side limit and we'll look at a right side limit. So let's first look at the limit on the left. The limit as x approaches 4 on the left side of this function. Notice that since we're on the left, we're looking at x values that are less than 4. So we're on this piece of our piecewise function. So what we can do is really look at this 3x minus 1. This is the same as the limit as x approaches 4 on the left of 3x minus 1. And now we can notice that this is one of our easy limits. We can go ahead and just plug in 4 and see what happens. 3 times 4 minus 1 is equal to 12 minus 1. That gives us 11. That's our left-sided limit. If we want to look at the right, we can do the same thing. We'll say we're looking at the limit as x approaches 4 on the right of f of x. And since we're looking at x values that are bigger than 4, we're going to look at this piece of our piecewise function. And so we'll say this is the limit as x approaches 4 on the right of negative 2x plus 4. And again, we can just plug in 4 and see what happens. Negative 2 times 4 plus 4 gives us negative 8 plus 4, which is negative 4. Notice the left and the right side don't match up, so we can go ahead and say this limit does not exist, since the left and the right are not equal to each other. If we found that the left and the right sides were equal to each other, then we could say, great, that two-sided limit exists. That's everything we need, and we could go on from there. So piecewise functions act the exact same way that they would beforehand. We're just going to have to really focus on the left and the right-sided limits before we can start plugging in x values here. So just keep an eye on that. All right, what we want to talk about today, though, is infinite limits, which we'll find out are going to match up with vertical asymptotes for the most part. So here's our example to start. Let's take a look at this function, and what we want to do is we want to look at the limit as x approaches 2 on this graph, on this function. So let's just do this graphically first, just to get some more practice with that. If we want to look at the left-sided limit, the limit as x approaches 2 on the left, let's just approximate this, see what happens. We're going to pick an x value that's on the left of 2, somewhere over here, so maybe I'll start here, and we're going to get close to this x value of 2 here. We're going to follow our graph, and notice that we can't ever cross this line because we don't want to push past that x value of 2. So we're just going to keep following our graph down this way. Since we're talking about infinite limits, it's pretty obvious that we can see this thing is going down to negative infinity. It's kind of weird, a little bit different than what we've seen before. Let's take a look at the right. The limit as x approaches 2 on the right of f of x. We'll start on the right side of 2, so maybe I'll start somewhere over here. And again, we're going to try and get close to this vertical line, this x value of 2, without ever crossing it. If we do that, we're going to follow our graph up, 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 and we're never going to get past there. And so we'll say this thing is going up to infinity. So this infinite limit is really trying to describe what's happening at this vertical asymptote right here. You probably have seen something like this before. If you went through college algebra here at Moraine, then you've probably seen this kind of a vertical asymptote limit behavior going on. But really what we're just trying to do is describe which way we're going at this asymptote. If, as we approach it, our function goes way down to negative infinity, or if, as we approach it, it blows up to positive infinity. This is really what's going on. What you can notice, though, that's kind of weird, is if you try plugging in the x value of 2, like if we were going to try and figure out this limit by saying, oh, let's just plug this into our function. Really, this is the limit as x goes to 2 of 1 over x minus 2. So if you plug in 2 here, what you'll notice is we get 1 over 2 minus 2. This is 1 over 0. Our function value does not exist here. Notice that that's a little bit different than the limit because we're just plugging in this value. With easy limits, we said that it's just the same thing. But what we'll notice here is that there's a bit more work that we have to do. But we'll notice that this thing does not exist. All right, let's just kind of summarize what we found. Here's our big theorem that we've got. We're going to try and figure out how to locate this. If we've got a function that is just a fraction of two other functions, basically it's a rational function, we're going to call these things. Then if the numerator p of a evaluated at some spot is not 0, but the denominator is, so basically what I do is I say f of a is equal to this number sign where I mean not 0 over 0, then we'll say f has a vertical asymptote at that x value here. And so we know that this limit is going to be an infinite limit. Notice that this doesn't work when we have 0 over 0, because that was our indeterminate form where we had to go back and try and do some algebra, and we could find out that sometimes those limits are fine. They're just kind of disguised. They're a little bit harder. So here, I'll use this number sign over 0 to say it's some non-zero number over 0. So in the last case, we had 1 over 0. Maybe we'll get -7 over 0 or something else. Here's some of the stuff that we know about this kind of case. If we find that there is an infinite limit like we saw in that last one, then right off the bat, we can say the limit doesn't actually exist. It's going up to infinity or negative infinity or something like that, but that's not a real number. We know that a limit only exists if the left side and the right side are equal to each other, but we also had kind of hidden in there that they were equal to some number. I think we called it L, but that had to be a real number. Infinity or negative infinity is not real. So we're going to say right off the bat, does not exist. But we've got more information. Anytime we have these infinite limits, what we want to do is go back and talk about the left and the right side. So we're going to notice that right off the bat, since that's an infinite limit, we know that the left and the right side have only two options. They're either going to go up to infinity or down to negative infinity. There's no other options in between. What we'll do is say that if both of them happen to go up to infinity, or if both of them happen to go down to negative infinity, like for instance, if we had some graph that looks like this, where see on the left side and on the right side of this asymptote, it goes upwards forever, then we could say the left side and the right side are both infinity, positive infinity. And so we could also say that the two-sided limit is equal to positive infinity. So let's just call this a. What we could say in this case is that the limit as x approaches a of f of x equals infinity. But this limit still doesn't exist. So this is kind of something that people have a hard time with every now and then. We'll say that if we have the two limits equaling each other, we can use that to talk about what the two-sided limit is doing, but this two-sided limit still does not exist because infinity is still not a real number. If we want to look at the left and the right sides, we can check those things pretty easily, graphically or numerically. What I mean by numerically is if we plug in some x values that, in our last example, were like close to 2, but a little bit smaller than 2, if you put in like 1.9 into here, what you'll notice is that you're going to get a super negative number. It's going to spit out a y value that's like really, really, really negative. And if you put in an x value that's close to 2 but a little bit bigger, like 2.001 or something like that, it's going to spit out a really positive answer. And as you pick x values that are closer to 2, it's going to spit out either more and more negative values if you're on the left, or more and more positive values if you're on the right. So once you know that there's an infinite limit going on, it's pretty easy to see what's happening. You can either just take a look at the graph, take a look at what that vertical asymptote is doing, since you know it matches up with a vertical asymptote, or just plug in some test numbers and see what's happening. There's some other kind of arguments that you can make. You can do something that I call like a sine argument. Say, well, if the number is a little less than 2, then this is going to be positive, this is going to be negative. Let's go back and just see that real quick. If we put in a number less than 2 here, we're going to have something like, so maybe I'll do my left-sided limit here. On the left, here, I'll do it. What we can notice is that if you put something in that's a bit smaller than 2 and you subtract 2, you're going to have a positive number on the top, 1, over something that's going to be negative on the bottom. Positive over a negative is negative, so that's negative infinity. Similarly, on the right side, still going to have a positive number on top because it's just fixed at 1. And if you put something a bit bigger than 2 in for x, then that number minus 2 is going to be positive. So you got a positive over a positive. That's positive, so we'll say positive infinity. Again, we know they're going up to infinity or negative infinity, so all we need to do is check the sign, which is kind of a quick and easy thing. But realistically, just take a look at the graphs, plug in some test values, see what's going on. Here's an example. Find the vertical asymptotes. So we're going to look and see where do we divide by 0, and we'll describe the limits. The easiest thing to do in this case is to just start by factoring this function out. So let's factor the top and the bottom. If you want, take a second to try and do that. Pause the video to make sure you know how to factor things, but I'll try and just do it relatively quickly. Numbers that multiply to get -4 are going to be -4 and +1. They've got to add to get -3, so we know that these are the signs. On the bottom, I'm going to factor out the negative to make it easier, and then I'm looking for numbers that are going to multiply to get 12 and add to get -7 if we pull that negative out. So that's going to be x minus 4, x minus 3. So right off the bat, we can look and see what's going on in the denominator. Here, we'll notice that x equals 4 is going to be an interesting spot, and x equals 3 is going to be an interesting spot. The problem is if you put 4 into this function, you actually get 0 over 0. This is one where we could cancel things out. So this is not going to be one of the vertical asymptote spots that we care about, because this one would give us 0 over 0, indeterminate form, cancel things out, try it all again. You'd find out that that limit actually does exist. So here, let's just take a look at this limit. If you plug 3 into this thing, you're going to get 9 minus 9 minus 4. That's going to be -4 over -9 plus 21. That's going to be +12 minus 12. That's 0. So here we've got a number over 0. So maybe I'll just go ahead and say, I'll use orange for this. I don't use orange a lot, but we'll say that's a number over 0 here. So we'll go ahead and look at the left side and look at the right side. I'll encourage you to figure this part out on your own. I'll give you the answer, though, just to make sure that you can see what's happening. On the left side here, this ends up going up to positive infinity. And on the right side, as x approaches 3 on the right, it goes down to negative infinity. We know already that this limit does not exist. Since these go to different infinities, one is positive and one's negative, we can't use one symbol to represent the way that this limit doesn't exist, so we'll just have to leave it here. If both of these were positive infinity or both of these were negative infinity, then we could add that two-sided limit here, but we should note right off the bat that this limit doesn't actually exist. That's everything we've got for this. take a look at some of these, see what's going on, see if you can figure out where these vertical asymptotes are.